of lectures for Jan, talking of exceptional polynomials and generation by conjugates. Thank you, Bob.
Thanks. I'm glad I'm able to do this. I'm very sorry I can't be there with everybody. I met Jan in the late 80s, I think. If I recall correctly, it was at a conference in Rutgers for Danny Gorenstein, and I think Martin was there as well. And then the next time I met him, I think was in Eugene, Oregon, when we were both visiting Gary's sites. And we hung out a lot when Gary wasn't free and spent a lot of time together. And my wife was there as well and met Jan for the first time, and they hit it off right away and were close since then. In some sense, she was sort of like an extra sibling to him. And in fact, she got to know Jan's sister, Noemi, very well as well, who I think also considered Shelley a sibling to some extent. So over the years, we spent a lot of time together all over the world, of course, in Cambridge quite often, in California very often, in Southern California. Michael Oshbacher very often would get an apartment for Jan and sometimes Ruth in Pasadena and get an office for Jan and me to work in. And also, of course, he was working with Michael and other people. Chris Parker was there one year. But then we spent a couple of months together in Jerusalem, all over the world. And the first time I came to Cambridge was in 1990 when I was in Germany for about 3 months. And Jan arranged for a visit to Cambridge and Oxford and London. And then there was also a conference in Durham that summer. And that was when we wrote our first paper. As Martin pointed out, he's first on the list, Cheryl's second, and I was third on that list. So, but I started later. So I was trying to catch up, and I still actually, Martin said he still has some papers with Jan to write. So do I, especially with Tim. And Jan and I still have some results to write up. So. Okay, this is not, okay, but anyway, so let me talk about the sort of the second project that we worked on was exceptional polynomials. And as Martin said, this came out of some problems in arithmetic geometry. So let me explain what an exceptional polynomial is. I'll just do it over a finite field. It makes sense over an arbitrary field, in fact, but the description is more geometric. But over a finite field, if you take a polynomial, and again, you can generalize this, it actually doesn't have to be a polynomial, but you take a separable polynomial of degree n, and you say it's exceptional if it's bijective over some extension field of FQ that's sufficiently large. Turns out if you can do it for some sufficiently large field, you can do it for infinitely many extensions. And in fact, all you really need is that for one field of size bigger than the degree of the polynomial raised to the fourth power. And then moreover, if you do that, then you can take any extension which is relatively prime to some an integer, positive integer C that you can determine in terms of the group theory. And this came up in Dixon in his thesis already in the 1890s at Chicago. And the main examples that one has are, the first one is just take a power of X. And if R is relatively prime to Q minus 1, then that's a bijective map. That's trivial. The second one is what are called Dixon polynomials. They basically come from the polynomial expressing cosine of n theta in terms of cosine theta. And there's a parameter that corresponds to alpha equals 1 in this setup, but you can take an arbitrary scalar alpha and it satisfies this sort of equation. So those were the two main examples that were known. So one would like, so there were various conjectures made about this. People really didn't know too much about it. Over the years, people got interested. Sure, got interested in this and proved some really nice group theory theorems that had some connections with it. So let me translate this to group theory. So if you're given a polynomial, this gives you a field extension of function fields, namely the rational function field kx over the rational functions in f of x, where k is the finite field you're starting with. You can take the Galois closure of this extension. So that's some transitive subgroup of Sn. And you might get some extra constants in there. So you might get a bigger finite field sitting inside the algebra in this Galois closure. You're not getting anything in the original extension, but over the Galois closure you might. I mean, if you think of the case of x to the r, you'll pick up rth roots of unity, for example. Let's consider the case where f is indecomposable. That is, this function field extension is a minimal extension. And one can reduce the problem essentially to that case. Okay, so here, let's get some groups in here. So let's let A be the Galois group of this extension. And let's G be the Galois group after you've shown on the constants. Let H be the Galois group of K over the extension field in the usual Galois setup. So H has index n and A, and you have a primitive permutation group because of the minimality on the quotient. So what you know is that A is primitive permutation group. You know that G is normal in A, and the quotient is cyclic because we're over a finite field. So it's just the Galois group of K prime over K. You know, and what's critical in here is that because f, the only point over infinity is infinity, because you have a polynomial, it's telling you that there's a subgroup of G, this normal subgroup, that's transitive on omega, and I mod OP of I is cyclic. This is called the inertia group of infinity. And there's one other condition that's a Riemann-Hurwitz condition, which in characteristic 0 is quite useful. In characteristic P, it's much more complicated to use. Now, when I saw this problem, I said, okay, well, you have a transitive subgroup. That means you have a factorization, and who knows about factorizations? So of course, Jan, Martin, and Cheryl had proved these wonderful theorems about factorization. So I said, okay. So Mike Fried asked me about this. And so immediately I said, okay, I'm going to ask Jan to get involved with this project. And so the three of us did get involved in this. Originally, Fried wanted to solve some very special cases, but I realized that the methods would really pretty much do the whole thing. As I said, Sure got involved with this. Look, if you take something over a polynomial with rational coefficients, you can reduce mod P for almost any prime P, and you can ask that that's exceptional for infinitely many primes. And these are called Sure polynomials. And Sure proved some very nice results about it. Fried sort of killed off the problem eventually. And one of the ingredients of this was Sure's theorem on primitive groups containing n cycles, that they're essentially almost all doubly transitive. In positive characteristic, the Riemann-Hurwitz formula is not all that interesting, but the factorization result is. And as was pointed out, Jan spent a year at Glasgow, and somebody else who was interested in this problem was Steve Cohen, who was at Glasgow, and he actually asked Jan about this, and I don't think they got too far. But the problem is that he asked the wrong question. He asked about this exceptionality, and not the factorization. And I'll say something about what the exceptionality means. Let's see. Actually, did I leave that off? I actually left off the exceptionality, which I'll say what that means in a minute. But so this factorization thing is really critical. The exceptionality is a weird condition. I meant to write it down, but what it says is that, so we have our normal subgroup G and the big group A, the quotient is cyclic. It says if you take a generating coset of that quotient A mod G, every element in that coset has a unique fixed point. So in particular, A can't be G because there are elements with fixed points always. So it's a sort of bizarre condition, and Cohen asked Jan about that, and it's not so easy to, it doesn't happen very often, but it does happen. But it turns out the factorization condition restricts you to various cases and allows you to solve the problem. And so the theorem is, if you have such a thing, then there are basically three possibilities. One is that the degree is the power of the characteristic, and our group is affine. The second is that n is actually prime, and G is either cyclic or dihedral group. So those are the two examples that I wrote down before. And then it turns out there's two more infinite families. So the geometric group, the G is PSL2, P the A, where A is 1, this is bigger than 1 and is odd. And the degree is this thing. So this H is basically, at least H intercept G is just the normalizer of a non-split torus. And it turns out you get examples there. Those are the groups, and people constructed a few of these once we knew all of these groups. There was work by Leinster and Zeev and Matthews and Cohen, et cetera. Now, so we got all the groups. So this was all of the group theory conditions and a bit more. And in particular, this gave a proof of a conjecture of correlates that if you have an exceptional polynomial of degree n over fq, then the GCD of the degree nq minus 1 is 1, which were in particular the examples that were known. I should say later on with Mike Zeev and with Joel Rosenberg and Mike Zeev, we actually classified all of not only the polynomial, the groups. So we had the groups, but we actually can write down the polynomials that correspond to those groups. And that was the nice thing about this problem. There were sort of three parts: translating to group theory, solving the group theory, and going back from the group theory to actually getting the polynomials. The ones, the degree of power of P is still open. So it's a nice problem to actually, I think we know what the answer is, but we don't have a proof of it. Another result that came out of these methods is sort of an interesting theorem. If you have a polynomial over FQ, and suppose it's indecomposable, as we were saying, but suppose over some extension field, some finite extension field, that's the only case that's interesting actually, it becomes decomposable. Then the theorem is either n is the power of P, or P is 7 and n is 21, or P is 11 and n is 55. And again, you can write down exactly which polynomials these are. And this comes from classifying groups with certain primitive permutation groups with certain properties. And it turns out there's only two. Okay. So as people have looked at exceptional polynomials for a long time, and as I said, it's really a problem in arithmetic geometry. It has connections with cryptography and coding theory, and there were tons of papers on this. Correlates, as I said, it started with Dixon, Shore, Freed, Cohen, Davenport, and there's all sorts of variations. Mike Zeev and Lenstra did a lot of work on this. And there's sort of a weak version of this where you don't assume that the degree is big, the size of the field is big, and what are called permutation polynomials, which is a much more combinatorial problem and much messier answer. So the second problem that I wanted to talk about was about it's related to several of the earlier talks where we were talking about products of constancy classes, products of normal subsets that Jan certainly was interested in. He did some really nice work with Gordeev in particular and Ehlers, I think. But anyway, here we're looking at generation. So we have some element in our finite, almost simple group is the most interesting case. And you want to know how many conjugates does it require to generate? What's the minimal number of conjugates you can find to generate or any finite, almost simple group? And this comes up in many interesting ways. For example, one of the nice consequences that we got out of our work, I'll say what the result was we classified all irreducible representations, or say primitive irreducible representations in positive characteristic for a group which contained bireflections. So of course, there's the classical work on reflections of Chevalier, Shepard, and Todd, starting in characteristic 0, but then also in characteristic P, there was Wagner especially, classified all of them. But so bireflections are just the next case up. You have an element that's trivial on a codimension 2 subspace. So the fixed space is it's codimension 2. Or really, you might as well just assume there's an eigenspace of codimension, at most 2. And so we classified all of these. And basically the answer is if the dimension is bigger than 10, it's only the obvious examples, classical groups and symmetric groups, or on the or alternating groups on the heart of the permutation module. And the result we proved, so there's sort of an obvious, so for the sporadic groups, one just can compute. And I think the worst case is 6, maybe for one of the Fisher groups. For the alternating groups, it's not so terribly difficult to do. So the main work was for the Chevalier groups, finite groups of Lie type. And of course, there's an obvious bounds. Like for example, for SLN, if you took, say, a transvection, well, it's fixing a hyperplane. So if you take 2 of them, it's going to fix a codimension 2 subspace. So you certainly would need at least n of them to generate. And for symplectic groups, similarly, you would need 2n. It turns out in characteristic 2, you actually need 2n plus 1. Because if you only have 2n, it turns out you're going to generate, you'll either be reducible or be contained in an orthogonal group. And then for exceptional groups, we proved, I think, something like the rank plus 3 always worked. And this has the application to these bireflection groups, and much more generally, we classified modules where there was an element with a very large eigenspace, roughly codimension, say, square root of the dimension. We actually classified all of them. And again, they're just the obvious examples for most part. For small dimension, you can, of course, get more examples. And this has consequences, for example, for what are called, generic stabilizers and regular orbits that Martin was talking about for linear actions. This came up, as I said, when we were looking at generic stabilizers, we wanted better results. So this led to some quite recent work that I'll talk about a little bit now, in saying, well, okay, so what about getting a bound in terms of the constancy class itself, or the element? So of course, transvections is the worst case, say for SL or a symplectic group. But what if you have an element that has a very small eigenvalues? And so the answer that we got, at least for the algebraic group case, and it does give results for the finite group case, for the algebraic groups, we get a bound in terms of the constant class. And basically, this was first done for SL by my student Spencer Gerhardt. And the answer is essentially what you would expect. If you have an element whose largest eigenspace is whatever it is, obviously the necessary condition is that you better have the intersection of those eigenspaces be trivial. And the answer is that's necessary and sufficient, except in one case, namely if you have two quadratic elements, for example, two involutions, obviously they're not going to generate. They're going to generate a dihedral group, and it's similar if you take any two elements with quadratic minimal polynomial. For the other classical groups, it turns out there are a few more exceptions, and we only consider elements of prime power order in general, or prime order most of the time. And so we get a result that's similar to that. That says in the case for classical groups, sort of usually the obvious bound is the right answer. And you get asymptotic results for the finite group from that says at least for Q sufficiently large, you get the right answer. Most of the time, you don't, you have to worry about the small cases, and it's not so easy to worry about small Q, although there are some times you can do. Let me just mention, especially for the exceptional groups. So for the exceptional groups, we got much better answers than Jan and I had gotten. So for example, for E8 of Q, we prove that 5 conjugates of any element of E8 of Q will generate, you can find 5 conjugates of any element in EQ over an algebraically closed field that will generate as in the Zariski topology. Of course, not as long as you're not over the algebraic closure of a finite field. As I said, Jan and I proved 11. And Tim and I are working on actually to prove that there are no exceptions for Q. So for any Q, we think 5 will work. I should say, Skip Garibaldi and I did analogs of this for Lie algebras related to questions of generic stabilizers for group schemes. R.E.A. Cohen and David Wales had a result for Lie algebras quite a long time ago. They proved 5 conjugates of a long root element will generate the Lie algebra for E6, E7, E8, F4 as well. And actually, R.E.A. gave a talk on this over Wolfog, and he asked how many generators do you think you need for E6? And I said 5. And he looked at me a little cross, but anyway. And then he said, well, how about E7? I said 5. And then he said, well, what about E8? I said 5. And the thing is, I had talked to Permet the day before, and he had told me what the answer was. So, but anyway. So Tim and I have a project to actually show that this works over the finite fields as well. For the algebraic group case, the nice thing about it is that you don't just, what Jan and I did sort of was find elements that generated. Whereas in the algebraic group case, what we do is we basically show that the set of conjugates, you just take the set of conjugates of your element, and you want to say the point is either almost all of them will generate in the algebraic group case, or none of them will. As soon as you have one, you get almost all for free. But we don't produce one because it's too hard to produce one. So what we just show is if it's not going to generate, we produce things that generate smaller things, but different smaller things. And then we show, well, if you look at sort of the generic thing in that set, and if it didn't generate the whole thing, it would have to have various properties, and that would mean there couldn't be, that would say most of them can't generate this other thing, these other possibilities. there's typically only finitely many, or at worst countably many other possibilities to worry about. So you just sort of eliminate the other possibilities, and what's left over is has to be almost everything. So so it's much nicer to work in the algebraic group case. But as I said, that then you can pass down to the finite case by using some variations of the Langevin theorem, which say that if you have an open subvariety of a set, then for Q sufficiently large, that's going to be almost all of the subset. In particular, will be non-empty. So you get at least asymptotic results and moreover probabilistic results as well. It says that almost all conjugates are the right number of conjugates will generate over the finite group. We'd like to make that precise, and one thing that comes up in that is that we know is this notion of fixed point ratios, which came up in some work that Martin mentioned with Jan about, which is related to the minimal degree. What's the ratio of fixed points? You take an element in a primitive permutation group, what's the proportion of points fixed? And so in the algebraic group case, you have a maximal subgroup, and instead of looking at the proportion of fixed points, you look at sort of the dimension of the fixed points on the coset space. And as long as that dimension is not so big, you can show that a generic tuple will not have a common fixed point, and so will not generate a subgroup of that maximal subgroup. And we know the maximal subgroups, and most of them you can sort of eliminate quite quickly. So there's, in some sense, only finitely many one has to worry about. Okay, let's see, how am I doing? I think I still have plenty of time. So, but okay, so Tim and I, so Gerhard did this for SLN. Then Tim and Spencer and I did this for the exceptional groups. And the point there was, with the exceptional groups, you really, all the big maximal subgroups, you have very good information about fixed point ratios, which translates to questions about dimensions of fixed points. And so you can get these results quite well. For the other classical groups, that's a preprint. It's on the archive. Also Tim and Spencer and I, and then Tim and I are planning on sort of translating this to finite. Okay. The other thing I will just mention, but I'm not going to say very much about it, and maybe I'll knock off a little early, is about the base size problem. So yeah, Martin mentioned it. I don't think I told Martin I was going to talk about this, so that's why he did. But compute the base size, and again, this goes back to the 1800s, and Martin and Pieber and various other people did some really great stuff on this in Cameron and Cantor. But Jan and I had started working on this as well, and Martin mentioned this result about the symmetric group. So Jan and I were working on this, and we're starting to get up there in age, so we were a little lazy. And Tim came along. Tim Burness came on the scene and was proving some great theorems about base size. And I think I met Tim, and I went to Jan and said, we should get Tim involved in this project. And Jan originally said, no, we should just do it. We want half of the glory rather than a third of the glory each. So, and I said, no. If we don't get Tim involved, we'll never finish. So we got Tim involved, and we did finish. So the symmetric group problem, that was the first paper. And then we've been doing working on this since. There was the algebraic group paper. We have a preprint on classical groups. Base size for classical groups is analogous to the symmetric group problem. And so I think hopefully that will get written up soon. Fortunately, Tim has a lot more energy than I do. So I'm very confident that we'll get finished. But it's really been a real pleasure working with Jan over all these years, but even more than working with him, it's just having him as a friend and a colleague. It has just been one of the joys of my mathematical life, but also my non-mathematical life. He was a great friend, and it was more like family than friend over the years. And as I said, we've seen each other over the world. And Peter Cameron mentioned that Jan arranged for him to be a fellow at Keyes. I was a fellow at Keyes, the G.C. Stewart Fellow one year, quite a while ago, and I had a wonderful flat in the building just across from Keyes on the top floor. It's the building right next to the Cambridge University Press bookstore. And so living in the center of Cambridge for a term was fantastic. There was a program going on at the Newton, and having lunch almost every day at Keyes was also quite nice with Jan. Talking to mostly non-mathematicians. They were mostly non-mathematicians at lunch. There was Jan and me and maybe one more mathematician at times, but and then we also there was a term in Jerusalem on asymptotic group theory where Jan and I had stayed in the same apartment building, and so spent a lot of time together. Every weekend we would go traveling around Israel. We'd rent a car and drive all over the place. So it's, I always enjoyed working with Jan, but even more spending time with them, and Ruth and Miriam and Shelley and Jan were very often. Jan would call, and I could tell if he called the house, it meant he wanted to talk to Shelley, not to me. So so I'm happy that I'm part of this. I'm not so happy that I not there actually in person. And of course, when this program was going on in 2020, I had really wanted to go to, especially to see Jan. That was one of the reasons I really wanted to be there. And I was going to be there for a workshop in March, and that's when sort of everything shut down. And I had already made arrangements to have dinner with Ruth and Jan, but unfortunately I had to cancel. And so I did not get to see Jan before he passed away in May of 2020. So let me stop here. And I guess I'll see people on Zoom next week. But anyway, thank you for letting me be a part of this. So let me stop.
Bob, I'd like to thank you. Can you hear me?
Yes, I can.
Oh, terrific. I'm next to this thing. I'd like to thank you very much for such a lovely talk and tribute to Jan, and for giving the last seminar for this day of lectures as tributes of Jan, who has been a wonderful friend and colleague to us. I don't know, I mean, shall I ask for questions? Does anyone have questions? It seems so beautiful as a final talk for today. Most of us are now going to go off and drink some wine, and so we'll remember you and the others on Zoom as we remember Jan. And I think I'd like to thank participants, speakers, the staff from the Newton Institute for filling in for all the times when we didn't remember to do various things. And so thank you all for participating in today's lecture day for while remembering an absolutely wonderful colleague and friend. Thank you, and perhaps we will close the day.